So let's start. So Sean, um, uh, let me just tell you about some logistics before we start. So I told you 75 minutes, and you can take questions as we go along, or
Yeah,
you can
absolutely.
refer it to them. So welcome everyone. Today's speaker is Sean Horan from University of Montreal, and we are very happy that he could accommodate his timings to speak to us. And so his paper is titled, well, the paper is not here, but the talk is titled Indecisiveness and Collective Choice. So Sean, all yours. Welcome again.
So can people see the title slide?
Yeah, yeah.
Okay, great. So this is a paper about indecisiveness and collective choice, and you might say, well, what are you talking about? The whole point of collective choice is to make decisions. And so I had to find, it wasn't easy to find, and I've always wanted to do this, but I found this quote from a German economics journal, which I think was a much bigger deal a while ago than it is now, by Wolf Gardner. And he said, hey, maybe there's something there's something informative about situations where, a collective decision can't get made. So there's a response in this journal. There's a back and forth about 3 different articles. There's a response by a guy called Claude Hillinger, who you probably haven't heard of. The first guy you have heard of, I guess, if you've worked in social choice. The second guy, probably not. He's maybe better known for some econometrics. But he says, hey, that's nonsense. You have to make a decision. So collective choice is about making a decision. And I'm sympathetic to both viewpoints. So from a, just from a philosophical standpoint, I'm sympathetic to both viewpoints. That, there really are situations where maybe the right thing for the society to do is to make no decision in terms of, not really being able to come to some kind of consensus. But at the same time, we really, the interest is in making decisions. Okay, so that's nice from a philosophical standpoint. But the truth of the matter is, and I think that in India, this is pretty clear, because if I'm not mistaken, in India, you have, at least at the individual level, ways of expressing, on the ballot, a way of expressing that you don't want to choose any of the candidates. So this none of the above as a potential choice on a ballot. So you can literally check that box off, none of the above. I think that's how it works, right? In Spain, they have a similar formal on-ballot procedure, which is what they call a blank vote or a white vote. Of course, there's other off-ballot ways that the individual can express, a desire not to make a choice. So spoiling the ballot or abstaining from voting. So this is at the individual level, and there are some situations where those individual mechanisms for indecisiveness can aggregate up, and actually you can, because of the existence of individual indecisiveness, you can get collective indecisiveness. But there's also a whole host of ways that, that the collective, even if the individuals are decisive, even if they make decisions, clear decisions, the collectivity doesn't. Okay, so how does that happen? So the most famous example maybe is this example of the hung jury. In Canada and the United States, you need, this movie, 12 Angry Men, right? You need the 12 jurors to agree on one of the 2 verdicts, guilty or not guilty. And if they can't agree, you have what's called a hung jury, and you don't make a decision. So you have to have a new trial. So that's just an example of a threshold requirement where, in some sense, the voting rule doesn't satisfy the law of excluded middle. So there's this gap where you don't, if you have 2 choices, there's this gap where neither one gets made. Sometimes that gets played out in terms of saying that 50% of the population has to, not the voting and not the voters, but 50% of the population has to vote for a motion in order for it to pass. So you also have a whole bunch of other procedural tricks, and you see these a lot. I don't know about in Indian politics, but I'm not that familiar. But in the United States politics, you see these things all the time. Tricks about how not to make decisions at the in legislative bodies. Okay, so there's no quorum for the meeting, so you see the representatives walk out and they say, "Oh, there's no quorum, we can't have a vote," or they try to pass a motion to postpone the proposal indefinitely, or they just start reading out pages of the dictionary. Okay, so these are other ways in which you can prevent a collective decision from being made. So the fact of the matter, all of this is to say that the fact of the matter is, whether you think that from a philosophical point of view, Wolf Gardner is right, or if you think from a philosophical point of view that Claude Hillinger is right, the fact of the matter is there are actual mechanisms in voting, in collective choice, that allow collectivities not to come to a decision. Okay, so non-choice is something that actually happens in collective choice. So I want to understand it better. Okay, part of this, and I'm not going to say much about this, but part of this is motivated by what I think of as a very uncomfortable dichotomy between collective choice rules that choose, nothing. Okay, that's a possibility, choose nothing, or choosing everything. So if you allow for the possibility of saying that all of the options are acceptable, I understand that that's different than saying that none of the options are acceptable. But so from a philosophical standpoint, those two things are different. But from a practical standpoint, they're not that different in some sense. So collective choice has this uncomfortable dichotomy between this choosing everything and choosing nothing. Okay, but I'm not going to say much about that after this. Okay, so I want to understand choosing nothing in the circumstances of collective choice. Okay, so the way I'm going to do that is very modest. I'm just going to take some procedures that certainly Bhaskar and probably many other people, Arunav, I guess as well, would be familiar. So collective choice procedures that are familiar, and I'm going to extend them to situations where these choice procedures allow for indecisiveness. Okay? And I'm going to try to extend them, and this is sort of more of an art than a science, right? I'm going to try to extend them in a way that I think preserves the most appealing properties from the usual setting where there's no indecisiveness. And then what I want to do at the end of it all is I want to sort of step back a little bit and say, did we learn something from this exercise? Okay. All right. So I have to give a few definitions, and then I'm going to jump right in. So the world that I'm dealing with is X. It's a finite set. Script X are all the subsets, where there's actually a decision to be made. So where there's two or more alternatives. And what I'm interested in are voting rules that don't use all of the preferences of the agents, but I'm going to start with some simple voting rules, and these are ones that only depend on, in some sense, some binary dominance relation over the alternatives. So the way to think about this binary dominance relation is, if X bears R to Y, that means that the voting population thinks that X is at least as good as Y. If Y bears R to X, then the voting population thinks that Y is at least as good as X. But if neither X, Y, R, nor Y, R, X, that means that in some sense the voting population throws up its hands and says, we don't know. Okay. And that's not to say that we're indifferent. There's a way to express indifference here, right? That's X, R, Y, R, X. That's indifference. Okay. So when there's in some sense, no relation between X and Y, that's the voting population saying, we don't know. Okay. So that's different from the classical setting in the sense that, you allow for this X, not RY, not RX. Okay. So the classical setting that has been most commonly studied is a situation of tournaments, okay, which means that you have a complete and anti-symmetric relationship among all of the alternatives. So as between any two alternatives, either the voting population strictly prefers one or strictly prefers the other. Okay. There has been some effort in this literature on voting to extend these, which are sometimes called tournament solutions, to a more general setting where the voting population doesn't express a strict preference, but expresses a weak preference. Okay. So these are two domains that I'm going to mention. So T is the domain of tournaments, and W is the domain of weak tournaments. So I'm going to refer back to these. But I'm interested actually in the domain R. Okay. And what are we going to do on this domain R is, well, we're going to define choice correspondences. For each R, we're going to define a choice correspondence. Okay. So a collective choice procedure is going to be a thing that you give me an R and you give me a set A that belongs to X, and I'm going to give you a subset of alternatives of A. Okay? And what's going to be different here than what people usually do, of course, is I'm going to allow for the possibility that, you know, the choice is empty. Okay? So there are two ways in which what I'm doing differs from what people usually do. At least in this special setting of thinking about these choice rules based on dominance relations, is that I'm going to allow for incompleteness, and I'm also going to allow for empty choice. Okay. All right. So these are the definitions, and now I'm going to jump right in. I'm going to start with what I think is maybe the most famous choice rule in this setting, and that's the top cycle. Okay. So the top cycle. The way it's always presented is that these are the things, you know, things that you choose are the things that dominate or indirectly dominate every other alternative that's available through a chain of dominance. So what we're interested in is we're interested in looking at the transitive closure of the dominance relation, and we just pick the things that maximize that transitive closure. Okay. So the definition I've written down here, you say, well, what have you done? I haven't done anything, right? I'm just using the usual definition of the top cycle, right? So that my definition in the extended setting is going to be the same one that you use in the tournament setting. The difference is going to be, of course, when I have incompleteness in the dominance relation R, it's possible that the choice here is empty. Okay, so that I've just used the same definition. You say, well, okay, so smart guy, you're saying you're going to extend all these procedures to a setting with incompleteness and allow for indecisiveness, but you haven't done anything. Well, I say, well, maybe that's true. I haven't really done anything, but this is not the only way you could have gone, right? So if I start with the top cycle as being the transitive closure of these strict dominance relations, there's other ways to extend that to these more general domains. I'm just going to give you two examples just so you understand that I'm not doing the only thing you could do. Okay, so I could just look at the strict component of the dominance relation. I could take its transitive closure and I can maximize with respect to it. Okay, that's a much more selective kind of rule. So it's going to end up choosing nothing a lot more often than the rule that I've written down. That's not the only thing I could have done though, right? So it turns out that when you have completeness, talking about the top cycle is equivalent to talking about Hamilton paths, okay? So what you're saying is, you know, a member of the top cycle, in the setting of tournaments, a member of the top cycle is an alternative from which you can draw a Hamilton path, which means a path through each one of all the alternatives using the dominance relation to think of it as an edge in a graph through all the other alternatives without repeating. Okay. So it turns out when you have a complete graph that talking about the transitive closure and talking about alternatives from which you can draw a Hamilton path, those are the same. But that's no longer the case once you go past you know, the world where you have, you know, completeness, where you extend to incomplete graphs. Okay, so these are two things that I could have done, and I'm not doing them. So just to tell you that I'm not doing them. Okay, so that's one solution out of the way in some sense. I just want to go naively and do exactly the same thing, or seem to be exactly the same thing as what's done in the classical setting. Okay. Another choice rule that pops up a lot that's more selective actually than the top cycle is the uncovered set. And sometimes, although not always, sometimes the way that I guess Bhaskar wouldn't define it this way, but and I'll say why in a second. But so whereas the top cycle thinks about taking the transitive closure of the dominance relation and picking the maximizers of that relation, the uncovered set, one way to define it is to cut that transitive closure off at 2 steps, okay, and define a kind of a more restricted binary relation, okay, which you dominate an alternative in 1 or 2 steps, but not more. So X bears R2A to Y if X are Y or X are Z are Y for some Z in A, okay? So that's one way you can define the uncovered set, is you take this 2-step transitive closure, and that's going to be my definition. That's the definition I'm going to give. Why is this sort of maybe less obvious than how you go about extending the top cycle? Well, that's because the way that the uncovered set is usually defined is in terms of something which is called the covering relation, which amounts to, I'm not going to be formal about it, but amounts to saying that X covers Y if X beats all the alternatives that Y beats. Okay. So that's an unambiguous statement in the setting of tournaments. Okay, so when I say beats, I mean dominates. Okay, and I could have equally said that X covers Y if Y is dominated by all the alternatives that X is dominated by. So in the setting of tournaments, those two things are equivalent. Of course, they're not equivalent once you go beyond the setting of tournaments. So there's many different ways to define covering relations in this domain W of weak tournaments, and many such definitions were given. For me, the really shocking part, the amazing part, is that it wasn't, and so these papers that I'm referring to, Board, McKelvey, Miller, they're all from the 70s, the late 70s. It wasn't until 2013 that Duggan actually proposed, John Duggan proposed the one that I've written down here, which to me seems like the most obvious one, but that's because I've written it down in terms of this 2-step procedure, okay? Whereas the usual way to think about the uncovered set is in terms of these covering relations, and there it's much more sort of unobvious how you go about extending the definition from the tournament setting to more general settings. So I'm going to use this definition of John Duggan's, which
just to clarify, the Duggan paper is about tournaments or for incomplete relation?
The Duggan paper is about weak tournaments.
Weak tournaments, I see.
Yeah. So he's that's right. So he's talked about, so actually as John Duggan often does, he has an exhaustive analysis of all the different ways that you can define the uncovered set in the weak tournament setting. And he describes all the relationships among these different solutions, and he gives characterizations, not axiomatic ones, but he gives some kind of some interesting results about all of those solutions. It's about a 50-page paper. Okay.
So Sean,
could you briefly reiterate what is this 2-step in the transitive closure?
What's that?
The 2-step transitive closure. Could you reiterate that?
So R2A, so you say X bears R2A to another alternative Y in A if X bears R to Y, or X bears R to Z, and Z is an A, and Z bears R to Y.
Okay.
So either directly dominate or dominate through an intermediary. And of course here I'm talking about R, which can be a weak notion of dominance, right? It's not a strict notion of dominance here.
So Sean, if you want to, so actually Jean-François Lallier and I have a paper on weak dominance,
I know.
1999, I think.
I know.
Social welfare.
Yeah, I know the paper. So what I'm going to do here that's a little bit different than what you guys have done, and actually what you guys did, right? In fact, you looked at a kind of a more complicated setting where margins can matter, right? Right.
Yeah, but we also defined one where
where the margins don't. Right.
You look at the sign.
Right. Okay. So what I'm going to do that's a little bit different than what you guys do is the characterization I'm going to give is entirely in terms of choice. Okay? So I'm not going to step outside of, you know, the setting of choice to give the. So you have one or two. I think it's actually maybe only one of your axioms, which is not expressible in terms of choice. And so actually later on, Sondeb Lahiri did used in some sense almost all of your axioms and then added another thing and gave a characterization, a choice-based characterization of the uncovered set. So you guys don't look at, so the other thing to mention here is that you guys do not look at the same definition of uncovered set as I've written down here. So your sign uncovered set is not the one I've written down here. I think it coincides with the definition of, or one of the definitions that McKelvey gave, but I don't quite remember. But the definition here I'm giving is a different one for uncovered set, so that's the other difference. And it's the definition that only John Duggan in 2013, at least to my knowledge, was the first to give. So that, I think, does that answer your question?
Yeah, I mean, go ahead. And
okay.
To be honest, I don't even remember what we did exactly. So.
Yeah. No, I hear you. Yeah. All right. Okay. So that's two solutions. And so now what I'm going to do, what I'm going to try to do is I'm going to try to characterize these two solutions. Okay. So I'll start with the top cycle. And okay, so the result is that if I have, so now I'm going to fix R. Okay, so I'm going to look at it as a choice correspondence. Okay, so when is it that I can say that choice correspondence is, in some sense, generated by some underlying dominance relation R in such a way that you're taking the top cycle according to the definition I gave? Well, that's if and only if the following three properties are satisfied. Okay. The first one is from a paper from 1973 by Smith, and it says this. It says that if it's the case that in any two-element choice as between alternatives in A and B, you never choose an alternative in B, well then when you're choosing from the union of A and B, you should only be picking things in A. Okay, this is Smith's property, which I think is a very appealing property, actually, right? So if even on an individual basis, none of the alternatives in B does well against any alternative in A, there's no way that the choice rule should be picking things from B. Okay, so this is sometimes called Smith consistency. I guess most well known by Moulin in this beautiful summary or survey. I guess not summary because there's many original results in there. Survey paper in social choice and welfare called "Choosing from a Tournament." So this is Smith consistency. Yes.
Doesn't Hervé also have a characterization of the uncovered set using?
I'm going to talk about that.
This axiom?
No, it's not this one. It's gamma. I'm going to talk about that. It's the expansion axiom, the weak expansion axiom of Sen. But I'll get there. In fact, I'll get there pretty much immediately. But before I'm going to get there, I'm going to say one other thing, which is I'm going to talk about this other property, which is sometimes called Condorcet transitivity, or this is at least a version of what's sometimes called Condorcet transitivity, which is a property that's usually attributed to Thomas Schwarz. And it says the following thing: if you choose X in the context of this other element Y, and Y is chosen from this other set B, then you should choose X from B union X. Okay, so if Y is good enough to be chosen from B and X is better than Y, then X is good enough to be chosen from B, union X. Okay, so this is sometimes called Condorcet transitivity, usually attributed to Thomas Schwarz. There's a little plus sign because actually Schwarz's property is a little bit different, and I'm going to mention that in a second. The other property that I need is sens gamma, okay? And this is the one that Hervé uses for the uncovered set. And that just says that if you choose X from two different choice scenarios, A and B, then you should also choose it from their union. So if X is good enough to be chosen from A and good enough to be chosen from B, then it should be good enough to be chosen from the union. So whatever reason you, and I guess they say, I mean, the mnemonic that Sen uses is about cricket, and I'm way out of my depth. But if you go look back at Sen, the mnemonic, he says, well, if you're the cricket champion of this place and this other place, then you should be the cricket champion of the two, or something like, I don't know. But that, you get the idea, okay? So this is a well-known property. So it turns out that those three properties are sufficient to characterize, necessary and sufficient to characterize a choice correspondence that can be rationalized as coming from the top cycle of some underlying dominance relation. Okay, so just a couple of notes. So what did I say? I said I want to write down ways, extensions of these rules that actually look a lot like the ones from the classical setting, and also sort of behave in terms of properties a lot like the ones from the classical setting. So I want to say something about what's the connection to the classical setting. I already said Smith, I already said Schwarz, but now I want to sort of be more clear about that. So for the classical setting, you can actually simplify the characterization by just getting rid of sens gamma completely and weakening the Condorcet property as follows, right? So mine had Y.
Sorry to interrupt, Sean. Could you just remind us again about script R and script W?
Okay. So the big domain of reflexive relations is R, script R. Script W is reflexive and complete relations, and script T is reflexive, complete, and antisymmetric.
Sorry, I forgot again. So W was without completeness, which is the...
No, it has completeness. It doesn't have strictness.
Doesn't have strictness.
Yeah.
You are looking at incompleteness, right? I mean...
Yeah, so R has incompleteness and non-strictness. W
okay,
has...
R is the one that... Okay.
R is the one I'm interested in. W has completeness, but not necessarily strictness. And T is the one that everyone is used to talking about, which is that you have strictness and completeness.
Okay, got it. Thanks.
Make sense? Okay.
Yeah.
Okay, so if you just think about the situation where you actually have completeness, you can throw away the gamma property because it's actually turns out that it's implied by the other two properties. And you can weaken the Condorcet property as follows, which is to say, what I said is, if X is good enough to be chosen over Y and Y is good enough to be chosen from B, then X should be chosen from B union X. Here I say, well, if Y is good enough to be chosen when X is available as well, right? Which wasn't necessarily the case for B, right? It may be that X is in B, but maybe not. Okay, so you can replace it with this, or you could do something different. You could replace it with this property, which is called gamma plus, which was suggested in a totally different context by Salant and Rubinstein. And it's sort of like a notion of gamma, except what you're doing is, with gamma, you're saying if X is chosen from A and X is chosen from B, then X should be chosen from A union B. what we're saying here is that if X is chosen from A, where Y is there, and Y is chosen from B, then X should be chosen from A union B, right? So in some sense, you're kind of getting at the notion of Condorcet transitivity, but it's a kind of much stronger notion because it's not just binary sets in the first part. That's one way to think about it. But the other way to think about it is that it's like gamma, except in the second term, you're replacing X element of CB with Y element of CB. Okay. So you're not just leveraging the fact that X is chosen from B, but actually just something potentially weaker that Y is chosen from B. Okay, so you can replace those conditions with this, and you can also do the following, right? Is that you can replace these Condorcet plus and Sens gamma conditions with one that's called beta plus, which was suggested by Board. So Board gave a characterization of the top cycle in the setting W with condition beta plus and the Smith condition. Okay, so that's 1976. What makes condition beta plus different from the usual beta condition is usually we say the following for beta, we say if the intersection of CA and CA union B is non-empty. Okay. Here we're just insisting on the intersection of A and C union AB. Okay. So it's a stronger property. Then whatever's chosen from A should also be chosen from this larger set. So this is to establish the connection, is that at least in terms of properties, I'm doing pretty much the same kind of thing that people have already done. Okay, so now I actually want to prove theorem one. What time is it? So I got plenty of time. Okay, so I'm going to prove theorem one, and actually the proof of theorem one just depends on this very simple lemma, okay, and that depends on this definition, right? So the definition is, okay, so I'm going to define something called the Topset covering. What is it? Well, it's a way of covering the set, any set A. Give me a set A. I can cover it with these little A sub i's such that the top cycle of any A sub I is non-empty. So that I'm, actually have some non-empty choice there. And it's the case that nothing from one component beats anything from the top cycle of another component. Okay. So you think, well, okay, this is a definition. Can you always construct such an object? Yes, you can. Okay. You can always construct such an object. And why is this object interesting? Because it allows me to give an inductive definition of the top cycle. Here's the inductive definition of the top cycle. So how do I know that X is an element of the top cycle of A? Well, if I can find a topset covering of A minus X, okay, such that X beats some alternative in each component AI, then I know that X is an element of the top cycle of A, if and only if. Okay. So in some sense, if I understand what the top cycles of these smaller sets look like, I can add X. Okay, and if these conditions are satisfied, I know that X belongs to the top cycle as well. Okay. So this it turns out actually is a generalization of a lemma that Lallier gave in his book for T. Okay, so what's the version of this lemma for T? Okay, what is a topset covering in T? There's exactly one topset covering in T, for any binary relation in T. What is it? It's the top cycle. Okay, so the lemma then just says that X is a member of the top cycle of A if and only if it dominates some alternative, which is a member of the top cycle of A minus X. That's Lallier's.
I have one question.
Yes.
So in the statement of theorem one, the capital R, it was not a there exists, or was it?
It's not what?
What's the there exists for this capital R? I mean, were you asserting existence of a binary relation R?
No. Give me a binary relation R.
Yeah.
Yeah. So which is reflexive. Okay.
Okay. So, yeah.
So X is in the top cycle for some given set A associated with this binary relation R, if and only if I can find a topset covering of A minus X. Such
No,
that
I'm wondering that in theorem 1, if all the axioms were true, then what is the theorem saying? So once these axioms hold for a function C.
Oh, you mean this? This one?
Yeah.
Okay.
So given the 3 axioms,
okay, in some sense, the revealed. Okay, so I usually work in decision theory. The way that you want to think about this in terms of decision theory is to say, if you give me a choice correspondence, okay, which is potentially empty valued for some sets, okay, I can rationalize the choice correspondence as being the top cycle of some underlying dominance relation R.
So that's there exists on capital R, right?
Yeah, that's right. So that's right. There's a there exists in front of the R, if you like.
And now coming to the lemma that you were discussing. So
yeah, which has nothing to do with the statement of the theorem, but.
Okay.
But here you give me the R. You give me the R.
And
I can check whether X is a member of the top cycle. You give me the R. Okay.
Right.
Okay. So does the unique top set covering property hold in your setting, or there can be multiple top set covering?
Many, yeah. So in fact, the uniqueness part, and actually maybe I should mention this. The uniqueness part are the alternatives that belong to the different components, the top cycles of the different components. Okay. So there's a unique set of alternatives which belong. So you give me any topset covering, and then you take the top cycle of each one of the components. However you pick the topset covering, you're going to end up with the same set of alternatives that are members of the top cycle. So the uniqueness part is the members of the top cycle. And in fact, so Thomas Schwartz uses that. This is the definition. This is the choice correspondence he looks at, which he sometimes called, I don't know what they call it. Sometimes it's called the admissible set. Sometimes it's called, he calls it BICH, I think, or some, he has these really weird acronyms, or gotcha or getcha. I mean, I get very confused. Okay, so Thomas Schwartz, this is the object he defines. He uses the fact that the uniqueness is in terms of what's chosen from these different components, and he says that's the thing I want to choose. Okay, that union of top cycles. Okay, all right.
So the notion of top set covering is defined given a relation R. Is that fair to say?
The notion of a top set covering.
It's given R.
Depends on the R. So you give me an R, and then I can check whether conditions I through 3 I's are satisfied or not. Right. So you give me an R, and you give me some covering of a set. Well, that's even part 1 of the definition. Okay, so this is all I'm trying to do is give some inductive definition of the top cycle, because I'm going to use this in the proof. Okay, so what do I need to do in the proof? I need to show that give me a choice correspondence. I need to first define this underlying R. So in going in one direction, I need to define this underlying R, and then show that I can build this choice correspondence T based on this R. Okay. And going in the other direction, you just have to show, that if you can do that, then those 3 properties are satisfied. Okay, but that's easy to check, that part. So what am I going to do? I'm going to define. So I'm going to focus on this hard direction, this difficult direction. So I'm going to define R. R is just the revealed binary choice relation. And I'm going to show that we have this equality by strong induction on the size of the choice set, okay? So, you immediately get this equality for A equals 2, the size of A equals 2. Why? Because that's just the definition of R that I've given. So let's look at sets that are larger. And there I need to do two things, right? I want to show if X is in C of A, then it's in TC of ARC, okay? So what I'm going to do is I'm going to take a topset covering, okay? And I'm going to suppose that the conclusion that I'm after is false, okay? In particular, that there's one component of this topset covering for which X doesn't beat anything in the top cycle of that component. And now I'm just going to define B as the top cycle of that component. And I'm going to put everything else that's in A in this other set called D. So now actually I've built these two sets, and those two sets satisfy the Smith, the prerequisites of the Smith condition, okay? Which is to say that nothing in D ever beats anything in B in a pairwise comparison. So it better be that what I choose, according to the Smith property, is only inside B and never inside D. But the problem is that X, which is by hypothesis something that I do choose, doesn't belong to B. Okay. So the hypothesis in this supposition that I made that X is not a member of the top cycle has to be wrong. So all I've done is I've used, notice I have three properties, and going in this one direction, which is to say that X is an element of C implies that X is an element of TC, I've only used the Smith condition. Okay. Now I'm just going to go in the other direction, right? Let's take an element, suppose now X is an element of TC, I need to show that it's an element of C. Again, I'm going to, since it's an element of TC, if you give me any topset covering of A minus X, it's going to be the case that X beats some alternative that's in the top cycle of each component, okay? We'll call those little alternatives AI with a star. And the induction hypothesis, here I'm actually using the induction hypothesis, which says that for smaller sets, I've proved this inclusion here. Whether it be for, these sets of A sub I, those contain less than A elements, okay? And of course, the binary sets also contain less than A elements. So it's the case that by the Condorcet property, X is in TC of X AI, and AI is in TC of AI, okay? This means by the Condorcet plus property, X is in TC of AI union X. So it belongs to each one of those things. Now I take the union of all of them, and I apply the Sens gamma property, and I come up with the conclusion that X is an element of C of A. Okay. So here, notice in this direction, I've only used, so to show the set inclusion in this direction, I've only used Condorcet plus and the Sens gamma property. I have not used the Smith property. Okay, so going in one direction, I use only the Smith property, and going in the other direction, I use only the other two properties. And if you look carefully at what I've done, you'll notice the following, right? It's baked into the proof that I've already given, which is that that if you give me a dominance relation, then the top cycle associated with that dominance relation is going to be the largest choice correspondence that's faithful to the dominance relation that satisfies the Smith property. Okay, that's the step one direction of the proof, and the step two direction of the proof is the second statement, which is that C is the smallest choice correspondent that's faithful to the binary relation that satisfies Condorcet plus and sends gamma. So actually the proof gives me more in some sense than the statement of the proof. It gives me this in some sense more sophisticated notion, which is to talk about largest and smallest choice correspondences that satisfy certain properties. And of course, when you marry the two, of course, it can be the only choice correspondence that satisfies the property, the three properties together. I should say, as a historical note, Smith shows exactly 1 for the domain W, and Good and Schwartz show exactly 2 for the domain W as well. But of course, they're instead of using Condorcet, right? Remember I said for W, you can replace Condorcet plus and Smith's gamma with just this other Condorcet property. So in fact, this result shows that those results, those classical results, extend in some sense in a very natural way to the setting I'm looking at. And in some sense, there's something very powerful in knowing, you have the largest or the smallest choice correspondences that satisfy certain properties. And the reason that that's powerful is, when I'm dealing with the uncovered set, which is what I'm going to do now, the uncovered set is a subset of the top cycle, so that I know that what I'm going to do is I'm going to have to add, in order to characterize the uncovered set, I'm going to have to add something to part 1, right? And I'm going to strengthen the Smith condition in a sense, but then I'm going to have to weaken the conditions in 2, okay, in order to characterize the uncovered, because it's smaller. What's interesting about these conditions in 1 and 2 is actually this way of dividing the conditions into 2 pieces. The conditions in 2 are usually thought of as expansion properties, okay? And the condition in 1, it doesn't look like it, it's not necessarily that obvious, but it is a contraction property. Okay, so what I've done is I've separated the characterization into 2 pieces. A contraction property, which I'm going to have to make stronger, and expansion properties, which I'm now going to have to make weaker. Okay, so let's do that. So I'm going to keep the Smith property, and I'm going to keep the sends gamma property, but I'm going to have to weaken, or I'm going to have to strengthen the contraction property. I'm going to do it like this, and I'm going to have to weaken having a lot of trouble with okay. I'm going to have to weaken the expansion property. Okay, so let's look first at the strengthened contraction property. What is it saying? It's like sends alpha, which says that if you choose X from A, and then you kill some element in A, then you should still choose X. Okay, but it's adding an extra condition here, which is to say, well, if that alternative happens to be better than X, or unrelated to X. Of course, I might choose nothing from the binary choice scenario. Okay, so when I get rid of alternatives that are better or unrelated to X, and I chose X before, then I still choose X. For me, this is actually a much more appealing property than sends alpha, which is to say that if somehow I was able to choose X despite the existence of seemingly better alternatives, that, in getting rid of those better alternatives, then I haven't diminished any reasons in some sense for choosing X. Whereas if I chose X from some set and I got rid of an alternative that's worse than X, maybe in some sense the basis on which I was choosing this alternative X was, well, I say, well, at least it's better than that other thing, so that's a good reason to choose it. But now if I get rid of that other thing, now maybe I don't have any good reason to choose it. So I think of this as a more appealing property than sends alpha for that reason. The Condorcet property here is a weak version of the Condorcet transitivity. Okay? So the characterization is that, right? So you give me a choice correspondence, I can rationalize it as coming from uncovered set procedure for some reflexive binary relation if and only if it satisfies Smith and undominated alpha from the contraction point of view, and sends gamma and base Condorcet plus from the expansion point of view. So as I said, Sondad Lahiri and Michele Lombardi give characterizations that are quite different than this for the situation of tournaments for Lombardi and weak tournaments for Lahiri. But they don't look like this characterization at all. Okay, so let's prove it. How much time do I have left? Okay, good. So let's prove this one too. All right. So the hard direction here is one. Is this one which I've written here, which is that if X is chosen from C, then X should be chosen from the uncovered set. Okay. Again, the necessity of the conditions, I'm just not going to worry about it at all. It's obvious. So I want to show the set inclusion in this direction. So I want to show C of A is a subset of UC. The other direction, and this is where I'm going to get to Bhaskar's comment, is covered by an observation made by Moulin. Okay. Okay, so there's two different scenarios you might have. One is that this alternative X is in some sense either dominated or unrelated to two different alternatives in A. Okay. When that's the case, okay, I can get rid of those two different alternatives, and X will be chosen from the smaller set in each case by the undominated alpha property. By the induction hypothesis, okay, CA is a subset. Now we're dealing with smaller sets, so CA is a subset of UC for these smaller sets. So what's the definition of uncovered set is that I can find a path either in one step or two step to every other alternative. So I can do it for all the alternatives in A minus Z1, and I can do it for all the alternatives in A minus Z2, so I can do it for all the alternatives in A. So X is an element of the uncovered set. The other possibility is that I don't have two such alternatives. So what do I do then? Well, then there's at most one. If there's none, if there's no alternative for which X is not chosen in the pair, I'm done, right? Why? Because that means X is weakly preferred to every alternative in A. Okay? So let's just suppose there's one. Well, now I use the Smith property. The Smith property says that, because of theorem 1, I know that my C has to be a subset of the top cycle. Because X is chosen, that means that, for this one problem, alternative Z, that there is some alternative Y, okay, which X beats, which in turn beats Z. Okay, so X now beats every alternative except for Z directly, and it beats Z indirectly by way of Y. So again, by definition of the uncovered set, X is an is an element of the uncovered set. So that's it. The other direction, as I said, in some sense is covered by the observation of Moulin, and Moulin's statement about the tournament setting is that that the uncovered set is the smallest tournament solution that satisfies Sens gamma. Okay. So that in some sense covers, and his argument works for not just tournaments, but it works for the setting I'm looking at too. Okay, so one consequence, again, of the way I've proved this is you look at it, right? Step 1 is to show the inclusion C of A is in UC. I've only used Smith and undominated alpha. The other direction, I haven't written it down here, but Moulin's argument only depends on Sens gamma, okay, and the fact that it's a tournament solution. So in one direction, I've used two of my properties. In the other direction, I've used the other two. And so that gives me this corollary here. So C is going to be the largest choice correspondent that's faithful to R and satisfies my two contractive properties. And C is the smallest choice correspondence that's strongly faithful to R that satisfies my expansive property. Or you can, instead of saying strongly faithful, you can say faithful plus Sens gamma plus base Condorcet plus. All right, so as I said, Moulin shows part 2 for the setting of tournaments. And this result shows that at least, nobody has an analogous result for part 1, but this shows at least that his way of characterizing the uncovered set extends quite naturally to the definition I've given here. Okay. In some sense, right? Right. So that means, Bhaskar, so this means that the definition you've given for the sign uncovered set doesn't satisfy this number 2, right? So your sign uncovered set is not the smallest choice correspondence that's strongly faithful underlying binary relation that satisfies gamma. So in some sense, it's not the smallest thing that satisfies gamma. It does satisfy gamma, from what I remember. Your sign uncovered set. So actually, it's.
I think it does. Yeah.
Yeah. So it's bigger. It has to be. That means it has to be bigger than the definition I've given here. So you can think of that as a good thing or a bad thing because my thing is going to be empty. I mean, you didn't define it for the setting of just dominance relations, but my thing is going to be empty when yours won't be necessarily. So that could be a bad thing. To the extent that that chooses something, mine is more discriminating than yours. But so I think that explains. Okay. All right. So I have. Oh, perfect. So I have a couple minutes left, and so now actually. Oh, I should say in the paper, I also extend the bank set to the setting that we're looking at here. I'm not going to say anything about that because the characterization I think is less neat. And from what I know, and Bhaskar might be able to correct me here, I don't know of any characterizations of the bank set in the classical tournament setting that are. So I don't have anything to compare it to. I can give you my characterization. But in some sense, I can't say, hey, look, it satisfies all the properties that are satisfied in the classical setting. So I'm going to leave it out. It's in the paper, which is still being written, but yeah. All right. So I want to step back and say, what have I learned in some sense from this experience? And this is not at all where I intended to go with this, but it turns out that the things that I think that I learned from at least these two characterizations can be kind of summarized this way. So let's take some dominance relation R. Associated with that dominance relation, you can think of all the ways. So remember, in R, there's between two alternatives. Sometimes there's no edge between bidirectional or unidirectional edge between two alternatives. I can think of all the ways of filling in relationships between two alternatives, so ways of completing the R that I have. And there's many such ways to do this, right? Because I might either say, for two things that are unrelated, I might say X, but not YRX. Or I might say YRX, but not XRY. Or I might say XRY and YRX. Okay, so there's three things I can do for any missing edge. So that's the way I can complete. I can also do something else with any given dominance relation is I can erase. So when there's a bidirectional edge, I can erase one of the directions. So I can make a weak relation strict. So start with a dominance relation. I can do two things to it. I can complete it in a variety of different ways, and I can kind of make it strict in a variety of different ways. So let's think of these C and A as being all the ways I can do these things. Okay, so now give me a choice procedure. I'm going to make these two definitions. So the first one is indecisiveness restrictive. So indecisiveness restrictive means that what you choose, okay, according to the choice procedure, is precisely all of the things that you chose from every single way of completing. So this is well defined. This object is well defined. So you can check there's a property. I just need F. Okay, and I need to understand what C is. So I can decide whether or not my collective choice procedure is indecisiveness restrictive. What does it mean? It means, in some sense, when there's no edge between X and Y, I'm going to be very conservative, right? And I'm only going to choose an alternative X if any way that I would complete, I would choose that X. Okay, so this is why I say restrictive. On the other hand, I can think of indifference permissive. Indifference permissive says that now let's resolve the indifferences. As long as there's one way in which I resolve the indifferences where X is chosen, it will be chosen from F. Okay? So I take these very opposite points of view when it comes to indecisiveness and indifference. So whereas in many settings, many choice settings, we think of incompleteness and indifference as being not that different, here I am treating them very, 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 very differently, okay? As differently as you can treat these two things. And so it turns out that the definitions I've given of the uncovered set and the top cycle are indecisiveness restrictive and indifference permissive. Okay, it satisfies both of these properties, which allows me to write both of these definitions in the same way here, which is, first let's complete. Okay, think of the things that get chosen from every such completion. Now let's erase one of the bidirectional edges. Think of the things that get chosen from one such scenario, and that's my top cycle. And an analogous statement is true for the uncovered set. So the extensions that I've given, so another way to put it is that I've given for these two objects, okay, treat indecisiveness in a very, very conservative way. And they treat indifference in a very, very liberal way. And actually, I think this is the right thing to do. But I don't know. And it certainly didn't start with this result, right? So one could start with such a result and ask, let me try to identify extensions that satisfy these properties. I didn't do that. I sort of started naively, and I came to this realization. And so I think it would be interesting to extend other tournament solutions along these lines. And I have done so. The extension that I've given for the bank set does, in fact, also satisfy these two properties. And so with 1 minute or so, a couple of minutes that I have left, I want to just write down the definition of the bank set, because I think it's interesting in and of itself, the definition of the bank set.
I have a question here.
Yeah.
So in terms of indecisiveness and indifference, can we also think of how it would impact the utility function of the payoff that agents receive once they have made the choice?
Well, one could do that, right? So the problem with doing that, in some sense, is that if you only have a partial order, it doesn't have the same structure as the real numbers, and so you can't. There's no way to talk about one utility. So if the individuals have this problem, so I'm looking at a situation where the collectivity has this problem. But if the individuals have this problem, and they have preferences that are partial order, you can't write down a specific, even in an ordinal sense, specific utility function. So I'm not right.
I mean, because of transitivity violations, is that what you have in mind?
Yeah, that's right. So the typical example is the example of just noticeable differences, semi-orders. you add 1 grain of sugar to the coffee, and then it goes from being completely sugarless to being very, very sweet. And it's hard to say at what point along the line it becomes sweet. Anyway, so I'm not sure. So there has been a lot of work trying to cash out the distinction between indifference and indecisiveness at the individual level. But yeah, I don't, in some sense, I don't say much about it here. But I guess you could think about it. And you could think about what yeah, I mean, you might think about what these solutions have to say about whether people would be happy with solutions in some sense that have these very stark treatments of indifference and indecisiveness.
Yeah. Okay. Thanks.
Okay, so I just want to give a definition of the bank set. And some of you, I mean, probably most of you are familiar with the top cycle, probably less were familiar with the uncovered set, and probably even fewer are familiar with the bank set. But one way to define the bank set is like this. I can define the set of externally stable trajectories. So you give me a set A and a binary relation on the restriction to A. And what's a trajectory? A trajectory is a transitive path through A. Okay, so that's what a trajectory is. What makes it externally stable? Well, what makes a trajectory externally stable is that for anything that's not in the transitive path, there's something in the transitive path that beats it. Okay, so if you want to think about what's a trajectory, think about a trajectory as being a long string with a couple, edges coming off of it, but the length of those edges coming off of it is only 1. Okay, there's not chains. There's not. So if you think of this as a tree, it's a tree, that looks like a pine tree with no leaves on it. It has things coming off it that way. Okay, but it doesn't have very long branches. Okay, so why am I defining these things? Well, the bank set is going to be the set of alternatives that are top elements in externally stable trajectories. Okay, this is a definition that has been used before by Miller. Okay, he gave him and co-authors, including Bernie Groffman, I think, gave this definition when they were talking about W. So no incompleteness, but weak dominance. The usual definition is different. Okay, the usual definition of the bank set is the following one, which is take trajectories and look at the longest trajectories. Longest in the sense that I cannot add another alternative to make a longer trajectory. Take the top elements of the longest trajectories. Okay. So the definition I've given is in terms of is trajectories plus external stability. The usual definition is trajectories plus maximality. Okay. It turns out in the setting that I'm looking at, maybe for obvious reasons, maximality isn't the right thing to look at. It's external stability. And so I was actually quite surprised by that. And so this, you say, well, that's just what you gave as a definition for the bank set. It's true, but actually you can define the uncovered set this way too. So how do you define the uncovered set this way? Let's look at subsets that have a weak Condorcet winner. So what that means is some alternative that weakly beats every other alternative. Now look at the ones that are externally stable. Okay, so the uncovered set, turns out the definition I've given of the uncovered set corresponds with the alternatives that are weak Condorcet winners for externally stable subsets for where such a Condorcet winner exists. So the uncovered set is precisely the set of alternatives that are Condorcet winners of externally stable sets. So the notion of external stability, which I use for the bank set, I'm also using here. I could give a different definition of the uncovered set using external stability. And Brandt, interestingly, uses maximality when he's looking at this more specific setting of tournaments. But again, maximality is not the right thing to look at here. It's external stability. You could look at maximality, but it doesn't give you the same definition than what I have here. But when you look at the setting of tournaments, whether you look at maximality or whether you look at external stability, it doesn't matter. They're the same. So what's interesting to me is somehow von Neumann and Morgenstern popped up in a place that I didn't expect them to see them at all. But there they were, and that's really all the time I have. I did try to think about extending other solutions, notably the Copeland set, but I'm having difficulty. Anyway, so food for that. Thanks so much for listening.
Thank you, Sean. Any questions?
Not a question, but I have a comment. Sean, you asked whether there is any characterization of the bank set, but I just typed that in Google and I got a hit. It's actually a paper by I'm one of the co-authors. That's Matt Jackson, Michel Lebreton, and I. But it's in a special domain, a set of where elements are budget allocations.
Yeah, I know the paper. Yeah.
So
okay.
That has a characterization.
Right.
But it's not in the the classicals.
Right. You've added right. Yeah. Yes. Okay, but I should. That's right. I'm going to look more carefully.
If there are other characterizations, I mean, you should write to Jean-François Lallier. He will know, or Felix Brand actually.
So I've talked to Felix about this paper, and he's not aware of any.
Okay.
Yeah. So one of the things that I wanted to do in the paper as well is that even the uncovered set, I thought that the best characterization was the one of Moulin, and this just relies on the smallest. This kind of smallest quantifier. And I wanted to give a characterization that got rid of that smallest quantifier. But I can't, yeah, right. But so Felix wasn't aware.
Mathematicians say that that's not not Hervé's characterization, but any such smallest or largest, that's not a very good characterization because you need to know the entire set.
This is why I agree with that assessment. So actually, what I was really after was characterizations where I could put the smallest and largest together, and then there's only one. And so I really worked hard to try to find, yeah. So the result I have for the bank set is the same kind of thing. It's the smallest, largest, and it's contractive properties that are stronger than the ones I have for uncovered set, and expansive properties that are weaker. And in each case, you have smallest and largest, so you only have one. Anyway, but it's more complicated, so I didn't want to get into it. But I welcome. I tried to think about the ultimate uncovered set and about the minimal covering set. These things are more difficult to. So I really did try to think about them. After I got the first two, I got ambitious and I thought, I can kind of do them all. I cannot. Yeah, I cannot.
What about the bipartisan set?
Oh yeah. So with some of these, right? After the top cycle, and I kind of got lucky with the uncovered set. It's actually very difficult to think about, in some sense, what's the right way to think about generalizing the definition.
Sean, at this point, I mean, isn't a standard approach to dealing with indecisiveness to think of it, through multiple orderings and then looking at the intersection? So the idea is that it has to be, all those decisions should go, all those rankings should go.
So when you write down, that's right. So what Arnav was talking about is utility representation of.
It may be related to your theorem 3, actually.
Right. So sometimes with these, Right, right. So in many cases, you can write down. So FAO has done a lot of work on these kinds of things, where you write down a family of utility function, and you look at the things that are maximizers of all of them.
All of them, yeah.
Yeah.
And that's, I think, without loss of generality, actually, you can always do that. And so you do
Uh,
that. So one way would be, for instance, take any procedure, any set that you have in mind, whatever, variant of whatever, uncovered set or whatever, and then you do it with the list, the list which will generate that indecisiveness, and then I guess you have the choice of. I'm not sure that the intersection of everything will be non-empty, and that may not be the right notion. Maybe you need to then look at the
with partial orders, right?
Yeah.
You always get you can always
so just look at the notion for every one of the things, everyone in that list, and then if you get something in the intersection, you should clearly, that really is salient in some way.
Right, and so this is, I guess, the usual connection to social choice is to think of this as Pareto, right? To think of each of these utility functions as being a one different guy. And
yeah, the oligarchy, the Gibbard oligarchy theorem, right? So that's exactly, that's, so whenever, each of those guys is a vetoer. So, I mean, if they all agree, then you have strict relation, and if they don't, then you have.
This makes me think that there's like, I know that Fuad Aleskarov has done a lot of work on these kinds of unions.
I don't know.
Collective choice rules that can be described as unions of intersections or intersections of unions.
Yeah.
Which he calls federations. I guess these are kind of like each constituency in the intersection is a kind of you need kind of unanimity, and then across constituencies you can have kind of, as long as anyone likes it, it's okay. There's a way to interpret these things. But yeah, so it turns out these rules are kind of this kind. But
I mean, the theorem 3 looks like some a thing like that, right? You're filling it in, then you're looking at something, and then you're looking at intersections.
Yeah. I was surprised, honestly. Theorem 3. I really just thought about this. This started off as a kind of like I said, it's a kind of a recreational project. And I just was like, I just wanted to write down some characterizations of these choice procedures. And then when I thought, well, what's going on here? And I wrote down theorem 3, I was sort of surprised, but in some sense I shouldn't have been. I should have been maybe thinking about theorem 3 from the very beginning. But we learn things inductively, I guess, right?
Sean, one question about your theorem 3. Can we go to that? Yeah, I mean, what happens if you interchange the order of the unions and intersections?
Oh, that doesn't
matter. To do that?
Yeah, you can do that. For me, it's just conceptually it makes more sense to put them down in this order, but it doesn't make a difference.
I mean, could you explain that why is this a natural choice in some sense? I mean, in terms of the main message.
It's a natural way to write it down, but maybe it's not. For me, it felt like the natural way to write it. But the point is that both of these rules satisfy both of these properties, right? So, yeah. But what's nice about writing it down this way, I think it's kind of the natural way to go from the setting I'm looking at to tournaments. I think, first you complete, which puts you in the world of weak tournaments, and then you make it strict, which puts you in the world of tournaments. So it kind of, whereas if you did the other way around, you would be going through domains that I didn't talk about in some sense. So that's the way in which I thought it was the natural way to go. But I don't know. I don't know.
Great. Thank you, Sean. So, is there
There was,
any other question?
I
Yeah.
think there was a question in the chat.
Oh, yeah. Sean, you want to look at that?
Okay, I will try. What am I looking at here? Oh, what is?
Or maybe I can read it out.
I gotta stop sharing. That's it. I gotta look at the chat. You don't need to call me sir. Is there a way to denote indecisiveness where in any set we assume that not choosing anything is also an option? Yeah, I haven't thought about it. Yeah, I think my gut instinct is yes, but that option is set specific. But again, this is just I don't really know what I'm talking about when I just said that. So yeah, so that's right. You have seen that kind of thing. There's lots of papers on individual choice that do this. They add a kind of dummy element or default choice element. Right. So you would have to define so you're saying I want to be maximizing. So I want to like look at the top cycle of some augmented set where I've added a default option, and I want to look at the top cycle of this augmented set. And my suspicion is that you would not be able to just add one alternative. This is why I say you would have to add set dependent alternatives. So it may be that you can rewrite all this stuff by augmenting the domain and adding one alternative for each set as the kind of so-called default for that set, and then extending the binary relation in a way that still allows you. I didn't think about it. I think that's quite complicated. I don't know. But that's my suspicion. If you can do it, you have to add more than one probably. But it's just a gut feeling.
Great.
It's a good question though. Thank you.
Yeah. Thank you everyone, and thank you Sean again. You should stay on because there are some meetings scheduled for you.
Yeah. Thanks so much for inviting me. Thanks for having me. I know it's late for you guys. It's Friday, time to party Friday night, I guess, right?
Not in these times, but yeah, usually it is. But, thank you, everyone. Thank you.
Thanks so much.